So good afternoon, everyone. Thank you very much for coming. We're very pleased to see you all here. Obviously, this is a sombre occasion, but also a joyful one somehow at the same time, very bittersweet. Before we start with the more formal proceedings of the seminar, John's son Hugh is going to say a few words.
On behalf of the family, I would like to thank both Informatics for hosting and SIXA for supporting this lecture today, and we are pleased to be here with you. It feels poignant and fitting to be here in the Informatics Forum, where Dad revelled in his work and enjoyed the company of colleagues and students. Dad was a firm believer in the sharing of knowledge and ideas, to be listening and thinking, and to be curious. This lecture is an appropriate and lovely way to remember him. I'm confident that John would have been very gratified to learn that today's lecture is being delivered by JP. We, as the family, are delighted too. Dad loved his work, but over the years, only so many colleagues were invited to the family home. JP was one who stood out, and not just because of his conspicuous height. I remember their animated conversations and the cheery company. I also recall one particularly memorable occasion where JP ably demonstrated yoga poses in the middle of the living room. Once again, our thanks for honouring Dad this way. We miss him dearly. I look forward to the lecture, JP, and I know John would too.
So I should have introduced myself. I'm not sure I did. I'm Jane Hilston, head of school. And we, as a school, and together with SIXA, wanted to organise this event. It's almost exactly a year to the day since John sadly and suddenly passed away. And like many people in the school, I can remember just where I was when I heard the news. And I know that I and the school felt bereft in the days that followed. And that feeling has continued throughout the year, although somehow does ease with time. We still very much miss John's wit and wisdom. I really got to know John well when we were working on the SIXA first proposal and then the early days of SIXA on the executive board, when we would take journeys around Scotland to other universities to discuss the SIXA project and things. And the best bit was always the journey on the train and chatting to John and conversations that went all over the place. So it's entirely appropriate at this time of year for us to come together again, this time to reflect and celebrate John's intellectual contribution. And it is with great pleasure that I introduce his friend JP de Ruiter. JP is currently with the Department of Psychology at Tufts University, Boston, where he is a professor of computer science and psychology. There can't be very many of those in the world, I don't think. His group combines experimental and naturalistic methods to address fundamental questions about language and social interaction, work that I know John would find very stimulating. Today, JP's talk is entitled Let Robots Be Robots.
So first of all, I want to thank all of you involved in this for this generous and honorable invitation. It's a great honor for me to be here. I'm really, really happy that I can contribute to a memorial of the great person and scientist John Oberlander. And thank you everyone who made this happen. This is the actually only picture I ever made of John. He was very elusive, and he was looking at me with this, "Oh, you got me there," but he's, well, he was eating. And this was in this building, I think. I just want to briefly talk about John and then go on into a scientific lecture that I hope John would have liked. The first time I met John was when I went to the kick-off meeting, which is a weird concept in in Grandland, the kick-off meeting in Brussels with the PIs for the comic project, it was called. And I was late because of the German trains. And I came into the room, and it was immediately obvious that everybody in the room hated each other deeply, which is kind of impressive because I was only 5 minutes late. So they had 5 minutes to start hating each other, and they succeeded. But in the center of this room, I remember seeing the guy from Edinburgh. I didn't know at the time he was the guy from Edinburgh. He was like this one guy who was serenely paging through the annex of the project, nodding and sometimes using his sonorous and hypnotic voice to calm everybody down until we reached the stage that immediate physical violence was averted and we could start talking. And that was deeply impressive, and I remember really being impressed by that. Basically, everybody was hating each other. I was staring at John doing his thing with the room, and that's how I got to know him. And I still have, if I'm in hairy political situations, which is more often than I like, I will always think, what would John do? And it helps. At the same time, John was a little bit of an enigma for me. Because on the one hand, he looked to me like the classical Victorian scientist, like as if he was the eccentric but charming philosopher in a Jane Austen novel. On the other hand, he was one of the most futuristic people I knew. So he was the first one who used a USB drive as if it was a normal thing to do. And we were all deeply impressed. And the other thing I remember is that he was the first person I met who had a computer screen approximately the size of Belgium. So these were things that, it's sort of an enigma that somebody who looked to me like a classic Victorian scientist was so oriented to the future. So to conclude this short memorial, I always felt that John was basically born a century late and died a century early. So let me go on to the topic that I wanted to talk about. So what I'm going to talk about is the idea, the old desire of mankind to do sort of recursive genesis and create machines in our image, which is sort of a thing that I actually, in the many projects I had with University of Edinburgh and John, was involved in. And I plead guilty. But I've come to think that that may not be a good idea. The vision is to make robots that look like humans and act like humans. Now, it seems obvious that if you have a robot, you want it to be convincing. I will try to argue here that this goal is, first of all, unachievable, it's unnecessary, and it's undesirable. I think these, if I manage to convince you of these three things, I think I have a strong case that we shouldn't do it, right? Now, this is related to the classical Turing test. The Turing test was an imitation game, and the idea is that if you want to really prove that you can do artificial intelligence, you convince humans that an artificial agent, like a robot, is actually a human. That's the general idea. And you do this in social interaction. And this was a really impressive idea, especially at the time. Because it is a great challenge, obviously, but also it avoids relying on human capabilities such as playing chess or solving math problems that looked impressive at the time, but aren't actually that hard to do if you know how to program a computer. And Turing had the vision to realize that there is something much harder than that, which is social interaction. And surprisingly, for most psychologists I meet at least, our social interaction skills are one of our crown jewels, cognition-wise. It's really hard to do. And it's one of my, basically 20% of my job energy is convincing computer scientists and psychologists that it's not trivial. You get people say like, well, how can this be hard? You know, you have person A, person B, and they download information into each other, and that's it. Why do you study this? You're wasting your life. Well, it isn't that simple. Now, the Turing test has practical applications as well, because you can use it to test if someone is a robot. That is practically useful. And you know these things that you get when you want to log into a site, these CAPTCHAs, where you have to prove that you're a robot. I always fail these tests, by the way. This is the one that I found particularly hard. I don't know if anyone has a solution, but I keep staring at it. Even now, I can't see what I'm supposed to type in, so I gave up. Another one that was slightly easier, but still slightly challenging as well, was this one. I'm not sure. I'm not a robot, I can guarantee you that, but this was difficult. Actually, I saw in the hotel, 2 days before, I saw a silly, maybe some of you saw it, on the BBC, a silly show, where the candid camera type of show, where a person was made to believe that she was going to the cinema, and it was actually not. But so they were playing her. And she went to the desk to buy tickets, and before she got the ticket, she had to indicate on a piece of paper which ones were the storefronts or something, to show that she was not a robot. And the thing that was worrying was that the woman, the victim of this prank, didn't even worry about this. She wasn't confused or concerned that somebody wanted to check whether she was a robot. So it's similar to this one. Now, is it possible, first of all, to develop human-like robots? Well, I'm going to address a few issues here. There's physical aspects. There's the pure appearance. How do we look? How does the robot look? And what can it do with its body? And the other thing is a mental thing, which is mostly its abilities. Now, we can, of course, make a robot recognizably humanoid, as in looking sort of like us, like this robot in my colleague's lab, Matthias Scheutz. It's a life-size robot, which successfully did a photo shoot with me and the student. And it looks sort of recognized that it's a humanoid, but it's, of course, it wouldn't fool anyone. There are other attempts that are more convincing. For instance, Ishiguro, who I always wonder which one is the real. It would be cool if the left one was the robot, actually, but I think it's the right one. But this is, of course, a little bit creepy as well. But on the other hand, yes, so this is really convincing. You have to hand it to them. This is a really convincing humanoid-looking robot. It's, in fact, even more convincing than some real people. So the abilities, however, are harder. It is absurdly hard to make robots do things that we found really simple. I mean, I don't think that 3-year-old children can do that all well, but pouring a cup of coffee without spilling anything, or from a what do you call, can, or making a bed using pliable surfaces is something that robots find really hard to do, and we find surprisingly easy. Where we are making progress, especially in where I live in Boston, there's a company called Boston Dynamics. They're very scary, their work at least. So this is a handle a few years ago. So as you see, that was quite an impressive form of acrobatics that was going on there. Now this robot, of course, looks a little bit like a crossbreed between a stroller and the Terminator. This, however, is Atlas, and it looks a lot more convincing. And look at what it can do. Now, I wonder if they make that a CAPTCHA at some point. Now, this is, of course, really impressive, right? I mean, the dynamics are very human-like, and it looks like human, and this is basically a gymnast at work. And So that's getting good. It's still, I mean, it's still hard to package it in. You would want to have that kind of ability in an Ishiguro kind of robot, but that's still not possible. We may get there at some point. Now, the mental abilities are a little bit harder, I think. And, well, then first I have to get something out of the way, which is that indeed machines outperform us at things like chess or Go or math, basically. But that's not really surprising, because similarly, machine always also outperform us at just moving very fast. So you can like, okay, they have the power, we don't, and therefore they go ahead. So that's not very surprising. However, interaction, as I will argue, is harder. Now, fooling people into thinking that an artificial agent is actually human is a common theme in literature and movies. So just to mention 3 of them, we know Blade Runner, there's now 2 of them. Westworld is now a series, and I don't know if you've seen the movie Ex Machina. That is, I think, the best one in this genre. It's chillingly good, with amazing acting. And I've seen it 3 times and it still doesn't get boring. Really scary. And the standard plot of these movies is advanced autonomous human-like robots develop nefarious intention, and this ends badly. Now this gives us a bit of a hint as to, is it a good idea to make human-like robots? Now, on the way to making these robots communicate like us, machine learning algorithms are very common and very often used these days, and they sometimes seem to make some progress, the statistical passage. So this is a small dialogue I had. I tested Cleverbot for a while for this talk. Hi there, how are you, Smiley? And I said, let's try some Australian idiom here. And how good, how's it hanging? And low. Fair enough, points for Cleverbot. There are still some issues with dialogue coherence, I would argue. This is another fragment to illustrate that. Do you think all people should go vegan? I asked. Me? Of course. Now why? See if we go into. Because you are clever, funny, and you make me laugh a lot. Okay, fair enough. That's an old reason to go vegan. I'm a nature lover, that's why global warming is one of the reasons that make me lonely. Here I lost it a little bit. So I did what we call in communication research a open class repair initiation. Open class other initiated repair. And I said, pardon? To which it replied, why do you like Chinese food? Which is just completely ignoring my repair initiation. This is not very human-like. And neither is the rest when I said I hate Chinese food and it said, what else do you love? There's some link there that is not getting on. So there's things that work well, things that happen a lot, like greeting sequences, it does well. Things that require going a little bit more into depth still are not convincing. Now, this also happens in human-human interaction, by the way, because this is a phone conversation I recently had with a presumably human. What's your last name? De Ruiter. No, that's hard. Can you spell that for me, please? I'm like, sure. D-E space. So that's B-H-D. And I'm like, oh, this is not going anywhere. So I'm like, okay, no, wait, let me try this way. First letter is D from Delta. Can you spell that? I hung up and waited till I got another operator. So, arguably, humans are sometimes not good at these things either. Robots that are like us. It's a tempting idea because, as I've hoped to have shown already, it's a very high bar and it's challenging. And it's also, if we manage, it's a good demonstration of how good we are at making robots. It is not a good idea because fooling humans is not actually that useful. I don't know, I can't find a scenario in which it would be useful to make people think that a robot is a human. Unless you, I don't know, want an MI5 and you want to have dispensable agents or something. It's also not ethical. After all, they are robots, so why would you fool people? And instead of trying to fool people, we may want to exploit their otherness. I mean, if you have an Atlas household robot, it can lift more than a human, which is actually good. If you lift old people out of bed into a new bed, it's good that they're strong. So why would they be human-like? They would be weaker. Doesn't make sense. So my thesis here is that we don't want robots that are like us. We don't want robots that can effectively collaborate with us. And that's a slightly different thing, or I would actually argue it's a completely different thing. Because in order to do that, robots must be accessible. I'll go into that. They must be predictable, and they must be accountable. Accessible. That means non-experts and robots must be able to communicate with each other. So you don't want to have a degree in robotics in order to communicate with a robot. You want to have normal, uneducated people, or not educated in robotics at least, be able to have a good communication situation. That means that the robots must be able to understand what we tell them, and we must be able to understand what the robots tell us. Sounds simple, right? And probably in order to get to this situation, some adjustments from both sides are necessary. We can't just put the entire burden, I think, on the robotics. There has to be, just as we have adaptations to new technology in terms of how to use a smartphone, we have to have some adaptations to robots. So one of my points is that there has to be a mutual influence there. Now, the first part, robots must understand us. This is an important point, we want it to either understand us with reasonable confidence or say it doesn't. Now, humans have a very natural built-in error correction protocol called conversational repair. And it's something we do approximately, 6 times per hour, very frequently. It's well documented, and it's a very, very handy thing we do in order to stay on the same page. If we don't understand each other, we can detect it, we can signal it, like go back, for instance, going pardon, or who, and then we exchange information to, no, I didn't mean him, I didn't, and so on, to resolve it. This happens all over the place. And this is very useful because it means that we don't diverge in our world models too much while we have a communication. And this is very difficult for robots, and this is actually now a new project in our lab where I hope to collaborate with the roboticists in our department to make this simple thing, at least knowing when you don't understand each other and then say something is wrong, or what Robin Hill once called the Wie bitte loop in German. That is something that we are very difficult. That's very difficult, and we are trying to do now by studying humans and trying to put the way humans do it into the robot. The other thing, we want to be reasonably certain that we understand what the robot means when it addresses us. Now, this may require a robot to avoid ambiguities that are extremely common in human-human communication. I am willing to have robots that are a little bit more predictable and boring in their communication in order to make sure that we understand what the robot means. For instance, stylistic variation, where they actually, even humans drive me crazy, my students. They write a paper and first it's participant, then it's player, then it's subject. I'm like, who are they talking about? But stylistic variation requires that we use a different synonym every time. I don't think a robot should do that. More problematic are pragmatic ambiguities. For instance, take this scenario. We are in a meeting, it's raining outside, and then person A says, did you get here by car? Now this is what we call an implicit request. And the person B then says, sorry, I got to pick up my daughter. On the surface, this doesn't make any sense, but for us, it is completely understandable. And there's an enormous amount of assumptions that we need to apply to make this make sense. We understand that this is an indirect request for a ride, followed by an indirect declining of that request and an account for it. It is totally natural for us. It is ridiculously hard for computers to get this. And of course we can try, but it needs a lot of background information. So this is difficult. And this requires knowledge about the context with humans and their intention, and about implicatures themselves. So the context being it rains and we're going home after the meeting, all these things that are obvious to us but not for the robot. Humans and their intentions, they tend to want to avoid getting wet. world knowledge. If you're in a car, you don't get wet. All these things need to be activated. And this leads to what computer scientists call the frame problem. What of the millions of things that a robot knows is relevant in this context? That's a tricky one. Now, we'll come to the second point. Robots must be predictable. We want future actions of our robots to be predictable. And there are, especially with robots that exceed ours. I remember we had a review meeting of one of our projects, a JAST meeting, Mary Ellen will probably remember that, where thankfully, unbeknownst to the reviewers, a gigantic Mitsubishi industrial robot tries to knock out one of our reviewers with a left hook and just missed it by like 3 millimeters. But because the reviewer was faced away, he didn't notice. And I remember some of us hurriedly shutting down the robot and going, phew. So my point being, yes, we really want this to be predictable because things can go really wrong. Now, third point, robots must be accountable. That means if our robot exhibits undesired behavior, we want to be able to do something about it. We want to fix it. Specifically, we want to be able to find the cause. Why did the robot do this weird thing? For instance, why did the robot try to knock out the reviewer? We still don't know. But, we want to be able to make sure it doesn't happen again. And ideally, by the users themselves. So you don't want to bring your robot to the garage. Okay. Now, if a robot screws up, basically, then we want to question its reasoning, its motives. Like, what was the cause of what was the robot thinking, basically, when it did X or Y? That's tricky. So there is this famous Asimov, the science fiction writer, had these famous robot laws. Well, the first law is do not harm humans. The second is do not harm yourself, unless this violates number one. And the third one is obey orders, unless doing so violates 1 or 2. Now, this looks simple and obvious and waterproof. It isn't. It is not that simple. In fact, Asimov himself had many stories he wrote about how it goes wrong. And you can imagine even if there's lawyers in the room, they will probably already find the loopholes in this. So, a possible way to achieve my desired predictable, accountable, and accessible robot is going to be difficult. And we know one thing from the good old-fashioned AI approach in the old days, the 80s and 90s, that just hard coding it, just programming it to work the way we want is not going to be sufficient. So what we need is the robot to learn from experience, like we do, preferably a little bit faster because we don't want to raise our robots for 18 years. Now, I wrote a grant application in 2008 with Alois Knoll from Technical University of Medford and John Oberlander, where we had the idea of giving robots access to a large database where they can record certain aspects, I won't go into technical details, but certain important aspects of their interaction in a large database. The idea was that then at least the robots can learn from each other. And they will continually update this database with their new experiences and use it to get better at interaction. This was actually rejected, the grant, I remember, because it was very funny. One reason was that we used the wrong programming language, which I thought was a really strange objection. So what is very in vogue these days is the concept of machine learning, which is a sort of a form of statistical learning. So you don't actually program things yourself, but you let the system figure out from a lot of data how it has to behave. And one of the most useful in interaction is the reinforcement-based machine learning, where you have data about a lot of aspects of the situation and a quality metric. And these will then lead to a optimal approach under the circumstance. So one of the methods that you can use for that is the POMDP, the partially observable Markov decision process. And you need a lot of interactions for that to work. And they're coded features, which is also important. And if you have some quality metrics, you can improve the robot's interactivity. This takes a lot of computer time, but then you have something that works. There are some problems with this approach, as we found out in one of our projects and in other projects that I did later. The problem for this approach is that we're actually not looking for a response by the robot that is some statistical extrapolation of correct behavior. We are looking for a response that is adequate in the here and now in the situation we're in. And oftentimes, POM-DPs lead to responses that are generally okay, but not specifically okay. The second problem is that it's hard to find out why a robot using this method did something wrong. We can have deep inspections of the weights in the training network, or the parameters. We can do experiments. Some people do that. They just do experiments with the robot and see, as if it's a human subject, and see how it responds. But we, of course, want to specifically know why that specific robot responded in that specific way in that specific situation. And that is sometimes a bit hard with statistical learning, because it didn't learn from a specific experience, it learned from a lot of them. And so it's very hard to fix problems if there are, because you basically have to collect more and hopefully more relevant data. Like if somebody keeps tripping over a banana peel, you may include a lot of slippery surfaces in the training set, and then maybe it will learn to avoid tripping over the banana peel. And this can be very slow and expensive. It's certainly not useful at the moment to do that online. Now, a proposed solution that I want to explore is sort of a hybrid solution where the core of the decision algorithm of the robot is basically rule-based. It's kind of classical symbolic rule application. This makes it accountable and predictable. But supervised machine learning as a method is used as an additional heuristic to sometimes find shortcuts in a computation that avoids the problem we had in good old-fashioned AI, where robots were doing the correct inference, but basically freezing because it took them too long to go through their database of possibly relevant facts. So, for instance, for finding the subset and rules of facts that is most likely to be relevant in a specific context, this could be used to optimize the system. You still have the accountability of the rule system, but finding the rules to apply is a bit faster. And this is related to the frame problem. So, for example, in one of the attempts in this direction, Chris Cummins and I have proposed a computational architecture for the recognition of elocution. That's the communicative intention of an utterance. I mean, linguists get all excited about sentences like, the cat is on the mat, and it's a sentence, but what you also want to know, if you hear that sentence in real life, the cat is on the mat, there's a question of, why is someone telling me this? What is the person telling me trying to accomplish? Is it a complaint? Is it a warning because there's a dog in the house? I mean, there's a reason for somebody to say that. And this is what's called the elocution or communicative intention. And it's really hard, actually, to get at a surface utterance. Take the example, are you by car? I have to get up my daughter. The intention is a request for a ride. It's a request. The other is a declination of a request, or whatever you call it in English. So that is not in the surface structure, usually. So you have to recover it. So that's why we made this model. It's called Airbus, and that's kind of a long acronym, which I don't want to get into. And it provides a probability distribution of what people want to do with their utterance of elocutions before they even say something and after they said it. Because that's the interesting part of the model. If I ask you a question, I can guess that you're probably going to give me an answer, whatever you say. This is Gaussian logic. So that already tilts stacks the deck towards questions. It can also be another question. If I say, can I have a packet of Marlboro? The other person can say, what's your age? So then you go into a stack-like structure and finding out, because before you can answer, yes, you can have a packet of Marlboro, you want to know you're over 18. So it's not a deterministic situation, but it is a situation in which there are reasonable guesses. Then you process the utterance, and then you do Bayesian updating, and then you have a posterior distribution, which is after the utterance. And the trick is, if the before you had said anything and the after you have said, so if your expectation and the later computation diverge too much, you invoke conversational repair, the process that I showed you before, where I said pardon to Cleverbolt because there was clearly a mismatch between what I expected and what I heard. So basically this is the diagram, and I don't want to go too deep in the technical aspects of it because that's not the kind of talk this is. But just briefly, there's a prior distribution of communication intention given the context and the signal. And the signals, these two things are checked against the database with conventions because there are certain conventions like hello is a convention. This resulted in a modified prior that incorporates the conventions. And then is just using normal Bayesian update. It's updated with the likelihood, which is the opposite of what we want to know, which is the probability of a signal given a certain intention and context. And finally, it results in a new and updated distribution, which you see at the bottom here. And if these two are very different, then you go, for instance, what? Or pardon. So this would have already, and of course after that the system can learn that in this context it actually could mean something else than we expected. So there's a kind of a learning loop in there. It's just one way of which you can implement the hybrid system that I just suggested. So Airbus could benefit from the approach that I had in this grant application because the tricky part is the estimation of the likelihood, which is the probability of a certain signal given a communicative intention and a context. And if you have that in your database of thousands of human-robot interactions, it is easier to estimate, and therefore it improves the accuracy. That's the idea here. And of course, this can be optimized using machine learning. I'm totally fond of machine learning if you apply it in the right way, by speeding up processes that we understand. Now, if we do something like this to get robots to communicate, this has really interesting implications for robot culture, for lack of a better term. Because robots and humans will adapt to each other, but importantly, robots will get information about humans interacting with robots, not with humans. So it's actually not learning how humans interact with humans, it's learning how robots interact with humans and humans interact with robots. That's what's in the database. And this mutual adaptation will lead to a certain buildup of information in that database. So the robot's interactional style, its social character, if you will be shaped by mainly by two things, which is the culture of the user community. If you use this database in Japan, it will be different from when you use it in the UK. Because of different expectations, different patterns of communication, different acceptance of robots and everything. And also, of course, the implementation decisions of the manufacturer. To go back to the user community, one of the projects I did with people from Edinburgh University, robot project, was that we looked at user satisfaction of the robot, and we had the idea of first asking before the people saw the robot what they expected the robot to be like, how good they thought the robot would be without having seen the robot. Sort of their prior, actually. And what we found out, to our slight bafflement, was that the German subjects were much more pessimistic about the robot's performance than the British subjects. Which is something that we didn't expect, but was clear from the data. Now, this could happen here too. So you get a different user community. Implementation decisions for the manufacturer are, of course, very important. How does it look? How does it move? What kind of hardware is in there? So these two are basically then creating a robot culture. So this could lead to prejudices and attributions. So you could have the conversation like, oh, your household robot's a bit grumpy. Yep, sorry, it's a Panasonic from Germany. That's, with culture come prejudice. One thing we know from social psychology. So to summarize and wrap up, the holy grail of social robotics is to make robots indistinguishable from humans. I want to claim here that it is probably impossible, not desirable, and potentially unethical. I think what we need instead is robots that are accessible, predictable, and accountable. And we could perhaps accomplish this by using a hybrid rule-based statistical approach, as I laid out. And we certainly would need a central repository of experiences, otherwise the learning will be too slow. This would lead robots to develop their own culture. And this culture will be influenced by the user community, design decisions by the robot companies, and maybe also at some point other robots they interact with, which is sort of the next step that robots communicate with each other. This is, for instance, something that could happen if that step is reached. And that's it. Thank you very much for your attention.
So thank you very much for a very stimulating talk. We're happy to take some questions. Please wait for the mic so everyone can hear you. Do we have any questions?
Thanks. Hi. You mentioned it a little bit, that actually what lots of people end up studying are human-robot interaction and the adaptive behaviour between robots and humans, not human-humans. The ideal is that the robot or computer is learning about humans, okay. How much really are humans aware of their behaviour with the robots? So, I mean, for example, with your car example, if a robot asked you that, you might just literally reply, yes, I came by car, rather than expecting them to have deeper understanding. But is that entirely natural? Are people just doing that spontaneously? Or are they thinking, it is a robot, and that's very much in their forefront of their mind? How natural is this becoming?
That's a great question. Can you hear me if I talk like this? Or yes? I'll try to talk a little bit louder. Yes, so, and I guess you all heard Robin's question very clearly. I think that's a very important point. We do actually, humans are known to address, sometimes wrongly, to adjust to their interlocutor very clearly. I don't know if you noticed, but often people speaking to foreigners who have problems with the language start speaking louder, which is usually not the appropriate response, but it indicates that they are aware that there's something wrong. People speak different to foreigners, people do speak different to children. And I remember at the inaugural lecture of Martin Pickering, he was citing an experiment where it was shown that people do more recipient design with a computer that looks very old, I think it was an MS-DOS computer, versus a more modern, maybe a Mac or something, or even more sophisticated than that. So people were shown to be, I think it was Holly Brannigan's study that did that, where that people adapt to the quality, the attribution of the computer. The same will happen with robots, and people will make mistakes. I mean, it's very tempting to ask Ishiguro to go for a beer and to realize that all it can do is smile and move along. Whereas there are robots in our lab, not my lab, but the lab of Matthias Schoitz. They're adjacent. Sometimes they escape and come into my lab. That look like the picture I showed you, but they're much more capable than Ishiguro is. So, and we have, of course, prejudice and adaptation, but I think that is a normal thing. And we do that not only with artificial agents, we do that with other humans as well. So it's a natural thing which we could exploit. And of course, if we find out if the robot goes, I know you want to ride, then we only have to do that twice, and the next time we know that the robot gets it. But if it goes very literal on us, then. But as I said, this is a range of behavioral variation that is also in humans. Some people need more literal information than others. So that's a completely natural thing. Thanks for the question. You decide.
Thank you. I really enjoyed your lecture, very thought-provoking. But I think I maybe missed the bit where you tried to convince us it was impossible. You certainly seem to argue that we're not there. And you sort of argued quite convincingly that it's quite hard, which I suspect everyone believes anyway, but what's the argument that it's impossible?
Thank you. So yeah, I was actually vaguely aware of it when I went through my slides before the talk, that this was maybe a missing link, so I'm grateful for you to point that out. There is a step there that, it's like this cartoon of Sidney Harris, and then something magical happens. I'll explain step 2. The thing is, if we need, it's hard to explain, let me think. So if we want to have, let's assume that we're going for the human-human. I think that's what you mean, right? The human-like robot. Yeah. I mean, I'm sure we can make a robot. We already have robots. But a real human, convincing human robot would have to have the same experiences and background knowledge as a real human. Not you or me, but a sort of generic human. Now, if you remember the scene from Blade Runner, where a robot, a very convincing robot, it's actually a human, I think, but playing a robot, is supposed to be a robot and is tested. And what they do is they have this test in the middle where they look at the emotional response, the physiological emotional response of that robot to certain questions. And I think after like 25 questions, the robot fails. Now, in order to reach that stage, you would actually have, I think, to have a robot go through the experiences that humans have in order to get there. We can't just decide, take your brain, look what is in there, and program that right away. So we have to do learning. If we do learning, we'd actually have to raise the robot, which is a bit of a problem because robots don't grow. And if we finally make a robot that grows and have the same organs and everything, then it becomes a clone. So in that case, can you then still say you build something? Or is it, I mean, we know how to make humans, you know? So if we claim that as a success, it's not the same thing. But if we want to actually construct something that is built on so many experiences, I think the experiences themselves will be so different from what a human that they still end up being different. So that's why I think, of course, maybe I'm wrong. I mean, I remember my father had to prove for his high school exam that it was mathematically impossible to go to the moon. He had to memorize that proof, and we had a giggle about that. And maybe I'm wrong in the same way. But the thing that I think is the hardest, apart from the outward experience, I think we can fix that. Although it's remarkably difficult to find motors that are as efficient as our muscular system. So that is a problem, but maybe we can get there, I grant you that. But the experiences, what makes us human is our memories, what our accumulated memories. And to get that all into, I don't know, it's something that I don't think any one of us will experience.
Hi, so I just want to ask a question about your Airbus model.
Yes.
Hello, JP, by the way.
I'll refer questions to Chris. Chris?
Oh, hello, Chris. Anyway,
Chris is not here.
so in the following exchange, the response is essentially a non sequitur. So imagine I'm from Essex or something. I go, windy, innit? And the response, windy, innit? And the response is, no, it's Thursday. Right? So there, the communicative intention is exactly what you expected. The response is an answer to the question. It's just the wrong question because they've misinterpreted windy for Wednesday.
Oh, so that's a speech error. So
Yes, so how does that...
Scott is dealing with problems of either hearing or understanding, and the hearing problems, they're already, they're at a different level, that's easier to fix. But of course, that could be, if you hear it wrong, you could have the wrong recognition.
Yeah, but I'd argue that it would be inappropriate in that context to say pardon. The robot should be able to reverse engineer how the question was misunderstood.
I agree, if that's possible, if there is a misunderstanding. But this is what you describe as a situation that we are studying extensively in our lab, and it's ambiguous. Sometimes you don't know if you misheard something. I actually exploited this once by saying something very funny or weird to a Dutch professor, who didn't expect I was speaking Dutch, so he thought I was speaking English, so he was like not realizing what I said. So these things happen. I do think we have made great progress. If you look at Google Home and Alexa, their word recognition is actually amazing. I don't know how they manage that, but it's the interpretation, the elocution that is not up to scratch yet.
Hi, I'm way up at the back.
Thank you.
Yeah. You said we don't want to wait 18 years, but actually if you could guarantee that we had a robot with fully human capabilities in 2036, I think that would be amazingly impressive. But more to the point, we only have to do it once. Every human has to learn individually, but once a robot has been trained, you can copy it to lots and lots of other robots. So maybe it is worth trying now and waiting 18 years and seeing what happens.
Absolutely true. Once you have succeeded in raising a robot, you can then copy it easily, we hope, into other robots. You still have to deal with the problem that I just discussed with the previous question, which is to get these exact experiences. And that is, if you learn them, a problem because you can't give the robot the same environment, and if you program them, it's a problem because we can't. So you're right, yes. So once you succeed, you have a model, basically, and that you can use, you can copy it, definitely.
Hi there. I'm just wondering, the focus obviously has been on verbal interaction, and yet we know from infants and from sort of human evolution that interaction has been through action before speech. So I'm just wondering how that fits in, whether there are restrictions by jumping straight to a verbal social interaction.
Sorry, restrictions?
So if we look at infants, they will be doing a lot of social interaction before they're able to sort of communicate verbally. And we know that through human evolution, that action and gestures preceded verbal in communication. So I'm just wondering whether an important step has been lost by jumping straight to verbal social interaction.
Oh, that's a misunderstanding. Because of limited time and because verbal interaction is our main and most important communicative channel as grown-ups. I just use that as an example because it's easiest to explain what goes on. But for instance, the Airbus model is, for instance, explicitly built to incorporate non-verbal interaction. So it's not dependent on verbal interaction. And of course, in bootstrapping as a communicative agent, children use lots of facial expression, eye gaze, gestures. We are aware of that. So I agree, it's an important thing. In order to get the information that a human needs in their brains, it needs to have these bootstrap procedures, which we could also try to emulate in a robot. Some people are doing that in developmental robotics. And at the moment, that's a very young science, so they're not very far, but things could come. One major problem is that we actually don't really know how children do it. But you're absolutely right. Especially at young age, it is very important, these cues. The idea, however, which is popularized in the 70s, that most of our communication is nonverbal is just bollocks. I mean, you can prove it in 17 different ways, experimentally, theoretically, that we do actually have that as our primary channel. So it's, I think, the most urgent one to work on in robotics. I mean, if you would have video recording, there is a video recording, of this whole meeting without sound, you would have no idea what was going on. But if you had a transcript, you know exactly what was going on. So, you know, that's why I believe it is the most important one. But how we get there is very dependent on these other signals, because the pre-verbal child has to get its information somewhere.
I know there are more questions, but I feel we should give JP a break. And he is going to be around for the reception afterwards, and you are all invited to come to the reception immediately following the talk. But just before we disperse and thank JP for the last time, I'm going to invite Chris Speed to give a vote of thanks.
Thank you, JP. Thank you. So it's my job. I'm Chris Speed. I'm Chair of Design Informatics, and 5 years ago it was with John we dreamt up a programme and a research centre and got an awful lot of work done. So it's my my opportunity to say thank you to a whole bunch of people. Really, thank you, JP, for coming over. Thank you, Jane, for hosting such a terrific space and opportunity. But Vina and the family, thank you very, very much for being here today. And of course, all of you who know and remember John so very, very fondly. So on behalf of the School of Informatics, Centre for Design Informatics and the wider community who value John so very much, can we extend a warm series of thanks to JP for coming over and presenting his work to today. Thank you. And like you, I guess you saw things, you saw identities, echoes of John within the talk. Occasions when you found John catching you on the stairs or catching you unawares with some extraordinary insight which allows you to extend connections which other people just couldn't do, actually. Thank you to Sixer, they made it all possible. And of course, again, thanks to Jane and Robin, who really helped make this thing happen. Well, of course, we're not just remembering John on this occasion. We've got a whole series of plans. It was terrific that just a few weeks ago actually, 2 students from Design Informatics both won John Oberlander medals for their work on the programmes. And it's great, again, with Vina presenting them on that occasion. And in the new year, we're going to work with the family to look to a permanent artwork with the family and try and find a way to commission it and where to install it, what form it will take. I have absolutely no idea. Something extraordinary, I'm sure. So I can't thank everyone enough for allowing today to take place. It's very close to the occasion when, as Jane said earlier, we were stopped utterly in our tracks 12 months ago. So well done. We've come this far, but we do it together. So once again, can I reiterate our tremendous thanks to JP for coming over, doing the John Oberlander Memorial Lecture, and thank you for being with us. And it's a great pleasure to have you all. And let's take time to have a drink. Thank you.